right, so next up in our series of lectures, turbine theory. So basic details of how turbines work. So we're going to be using this when we deal with microturbines in the next couple lectures. First off, we have many gas turbines, usually in the megawatt scale for large power plant installations, making power. These convert fuel energy into mechanical shaft power or electrical power. Basic consists of what's called a gas generator section and then a power conversion section. So we're mainly going to be looking at the gas generator section of them today and figure out how those work. And then after that, you can add to it a shaft to turn whatever you want to get shaft power out of it, or some sort of power conversion at the end of it. So the gas generator section generally consists of three components. There's a compressor, usually with a low pressure ratio, something like 4 to 1 or 5 to 1. Second component is a combustion chamber, and then third component is a turbine. And then I can get different types of these gas turbines by adding various inlet and exit conditions. So again, around my gas generator, I'm going to have some sort of inlet and some sort of exit, and what I put on the end of the exit basically determines what it does, whether it's a jet engine, whether it's a turbo shaft type of engine, which is going to create shaft power, whether I have some other electrical generator at the end of that. So again, the focus for us is the gas generator section, the part with the compressor, combustor, and turbine. And so standard station numbering, air comes in at point 2. Point 1 is for the inlet, so whatever we put at the beginning of that, that's why it doesn't start at 1. So point 1 deals with whatever is at the beginning of this. So point 2, air comes in, the part we care about, gets compressed in the compressor, obviously, between sections 2 and 3. Section 3 is where the combustion starts. So there is where fuel is added. This energy, high pressure air, is then burned in there, getting energy out of it. That energy then turns the turbine, and that turbine usually has two jobs. Its first job is to turn the compressor, and the second job is to add energy to whatever system is placed beyond that. So beyond point 5, I have my shaft or some electrical energy generation device. And so whatever energy is left over after the turbine turns the compressor goes to power those devices over there. So turbine between points 4 and 5. The thermodynamics behind the gas generator operate off the Brayton cycle, the thermodynamic process used for an ideal gas turbine power cycle. So start off, again, coming in at point 2, air comes in, then gets compressed, and then ends up at point 3. So through the compressor, I'm assuming for the ideal case that this is isentropic compression, so constant entropy as that happens. And then in the combustion chamber, the burner, between section 3 and 4, I'm again, for the ideal case, I'm assuming this is a constant pressure process. Then from 4 to 9, 9 and 5 were the same thing in the previous drawing. So I'm assuming there's nothing after the turbine. So point 9 is generally the exit point. And so the turbine goes from 4 to 9 in this drawing. Again, assuming it's a constant entropy process. And then constant pressure back to my entrance condition, point 2. So you can see it here in the schematic diagram. And air comes into my compressor, and then end up at point 3, go through my heater, and that's where fuel energy is being added in. So I have this additional heat addition from the basically chemical energy of the fuel. It gives me to point 4, then I go through the turbine. In that turbine, 2 jobs. First thing is to turn the compressor, so I need some sort of work come out of that W.C to turn my compressor, and I also get some net work out, whatever's left over. So again, this is the ideal cycle. I'm assuming that I have reversible and adiabatic processes through the compressor and turbine, so 2 to 3 and 4 to 9. Constant entropy processes, reversible and adiabatic. And then again, I'm assuming that 3 to 4 and 9 to 2 are constant pressure processes. So looking at the energy balance over this entire cycle, each process I'm going to have some energy associated with it, which is basically given by the temperature differences between the 2 points. So Q coming in into my heater, that is from my combustion chamber from 3 to 4. So the total energy will be T4 minus T3 times m dot NCP, so mass flow rate of air going through this engine, gives me the total heat coming in or energy added to the system. I have some Q out from the cooler part of this, so again going from 9 back to 2. Generally the temperature coming out of these things is still fairly hot, hotter than it is coming in. So T9 minus T2 gives me the energy coming out. And then work on the compressor. Again, I need to compress my gas from some temperature T2 to some temperature T3. That's going to take some energy. Amount of energy is, again, T3 minus T2 times m dot Cp. And then the total work that the turbine can do, again, temperature difference 9 to 4. So m dot Cp T4 minus T9. That's my total work from my turbine. So these are all written in terms of whatever gives me the positive value. So T4 is generally hotter than T3. T9 is bigger than T2. So these are all given as positive numbers. Then total work out. Again, for my turbine, I have the total work from the turbine, WT. I need to take away whatever work was done on the compressor. So WT minus WC is my total work out based on these equations. That's m dot Cp, T4 minus T9, total work from the turbine, minus T3 minus T2 work that the compressor took away. And so that's my total net work out. You can define thermal efficiency standard way. So thermal efficiency is work out divided by heat in. And so the work out, as we saw from the previous slide, m dot Cp T4 minus T9 minus T3 minus T2. And then Q dot in, as we saw going into the combustion chamber, m dot Cp T4 minus T3. M dot Cp is going to cancel out. I have a T4 minus a T3 up here, so those can cancel out and just get a 1. Then what's left over on top is a minus T9 and a minus minus T2. So I have a minus T9 minus T2 over T4 minus T3. And then here's where my assumptions come in. So I'm assuming my processes are either isentropic or at constant pressure. So if you remember, from 3 to 4 was a constant pressure, so P3 and P4 are the same thing. From 2 to 9 is a constant pressure, so P2 and P9 are the same thing. That way P3 over P2 is the same thing as P4 over P9. And then from 2 to 3 and from 4 to 9, I have isentropic processes. So isentropic process, I get the relationship that the pressure ratio to the gamma minus 1 over gamma power. So gamma is, again, this ratio of Cp over Cv. For air, gamma is generally 1.4. Those guys are constants essentially, so I can set those equal to each other. And then again, isentropic relationships, P3 over P2 to the gamma minus 1 over gamma is just the temperature, T3 over T2. Same thing for pressure, T4 over T9. So now I can set up this temperature relationship that T3 over T2 is equal to T4 over T9. And so going back to my thermal efficiency, thermal efficiency we had up here, 1 minus T9 minus T2 over T4 minus T3. Basically what I'm going to do is from the top, I'm going to pull out a T2. From the bottom, I'm going to pull out a T3. So instead of having T9 minus T2, I have T9 over T2 minus 1. Instead of having T4 minus T3, I have T4 over T3 minus 1 again. And then T9 over T2 is the same thing as T4 over T3 from these pressure or temperature relationships down here. And so basically this whole thing again is the same. So that whole relationship just becomes 1. So I'm just left with 1 minus T2 over T3. And then T2 over T3, I can go back to the pressure. So that's the same thing as P2 over P3 to the gamma minus 1 over gamma power. And then I can define this pressure ratio PR to be P3 over P2. And then my thermal efficiency is just given by that one quantity of the pressure ratio, P3 over P2. So this represents the pressure increase from my compressor. So if I have a 4 to 1 or 5 to 1 compressor like we talked about before, that'll just be 4 or 5, whatever it is. So that basically gives me thermal efficiency just in terms of what compressor I'm using. Another thing that's useful is find the maximum work. So I'm going to get some work out of my turbine no matter what, but it's always good to have the maximum work out of it. You can find the maximum work simply by taking a derivative. So d work divided by dt3. So derivative work with respect to the temperature T3 after my compressor. For my ideal cycle, I'm assuming I have a fixed inlet temperature, so T2 is a constant. I'm also assuming I have a fixed exit heater temperature. So after my burner, I have some temperature T4. Essentially, I can play with this parameter. This is basically determined by what my combustion chamber looks like, how much energy I'm adding to it. So basically, whatever combustion chamber I use determines the value of T4. And so I can fix that as a constant essentially. Then what's varying in terms of this maximum work is my compressor. So what compressor ratio do I have? That's going to determine what T3 is. So T3 is my variable of interest here. So taking my equation for shaft work that we had before, m dot Cp T4 minus T9 minus T3 minus T2, and taking the derivative with respect to T3, and setting that equal to 0. So setting it equal to 0, I don't have to worry about this m dot and Cp. I can just divide by those and they go away. Then what I have is a dt4 dt3, but T4 is assumed constant, so that's just 0. I have a minus dt9 dt3, a minus dt3 dt3, and then again T2 is assumed to be constant, so the derivative of that again is 0. So I'm left with a minus dt9 dt3, and then this derivative is just 1. So really the only thing I need to worry about is what is this derivative, temperature 9 with respect to temperature 3. And temperature 9, I know depends on temperature 3 because I have this temperature relationship that we derived a few minutes ago. T3 over T2 is T4 over T9. So solving that for T9 gives me T2 T4 divided by T3. And now we can take the derivative of that with respect to T3 and get negative T2 T4, the constants, divided by T3 squared after I do the derivative. So I can plug this into my maximum work condition, minus dt9 dt3 minus 1 equals 0. So plugging that in for my derivative, minus signs cancel. I have T2 T4 over T3 squared. Move the 1 to the other side. That has to equal 1. Now I can solve for T3 over T2. That's what I want to solve for. So doing that in this equation, moving the T3 over, dividing by T2, and dividing by 1 more T2 to give me T2 squared. I'm left with T4 over T2 on the other side, and then take the square root. So T3 over T2 is the square root of T4 over T2. And that's where I have the maximum amount of work. So as long as my temperature ratio through my compressor is equal to the square root of the temperature coming out of the burner divided by T2, that's going to give me the most amount of work possible out of this turbine. That situation of T3 over T2 equaling the square root of T4 over T2 also corresponds to the maximum area inside the TS diagram. So that's another way to find the maximum energy, or maximum work, I mean. So now we know how or where, at what temperature, the maximum work occurs. Also good to know what that actual work actually is. So what is the value of that work? So again, we can go back to our work equation, m dot Cp T4 minus T9 minus T3 minus T2, and plug back in for T3 over T2, the relationship we had before. So to do that, easiest thing to do is divide by T2. So I have m dot Cp, take the T2 out, and then I have these temperature ratios, T4 over T2, T9 over T2, T3 over T2 plus 1. And again, here's my relationship I want to put in. But before I do that, remember that T9 is also going to depend on T3. So I should actually replace T9 with his T3 version. So T9, if you remember, was T4 T2 over T3. So that guy becomes that. And then, as I said, I have T3 over T2 here. So I'm going to replace it with the square root that we had previously. There's also one here, though. So I also want to place that guy as well. So here I have T4 minus T2 minus T4 over T2 here, the square root, which is upside down in this case, T2 over T4, and then the one we had, T4 over T2, plus 1 again. And then here, I have a T4 on top, square root on the bottom, opposite there. So basically, this is just the square root of T4 over square root of T2. So I have first term, T4 over T2, minus this guy cancels out to the square root of T4 over T2. This guy is square root of T4 over T2, and then plus 1 at the end. So basically I have two of these guys in the middle. So T4 over T2 minus 2, square root of T4 over T2 plus 1. And then this guy is just a binomial. So if I can basically factor him out into T4 over T2 square root minus 1, if you FOIL this out, again, you get that. So maximum workout, m dot Cp times T2, square root of T4 over T2 minus 1. And again, just depends on the two temperatures, which I technically know. I know my inlet temperature, and I know my burner temperature coming out. So that's for the basic Brayton power cycle. There's three common variants of this. There's the free power turbine, and that's one we've just seen. That's one we've just been analyzing for the last little while. The two other variants are the reheat variant and the regeneration variant. So we'll talk about those. So the reheat variant essentially adds another combustion chamber and another turbine at the end. So after it goes through the standard cycle, after 0.5, there's another burner section called the reheater with some more Q reheat coming back in. So you're basically adding more energy to the system, like by having a second burner. And then this first turbine basically has only one real job, and that's to turn the compressor. Whatever comes out of it, again, gets reheated and then goes into the second turbine. So this is usually called the free power turbine. First one's called the high pressure turbine because the gas is coming out of my first combustion chamber at high pressure. And so basically have two different drops in my TS diagram. So standard 1, 2, 3, 4, 5. Then instead of going back down to 2, I then go up to 7, and then in the same sort of constant pressure burning process, and then down 7 to 9, again, constant entropy process there. So just have an additional one of those sections for my reheat variant. Because I'm adding heat to this, additional heat to this, I'm going to have a reduced thermal efficiency because I have more energy going in essentially. I do get more energy coming out as well, but proportionally it's not quite the same. So overall thermal efficiency for this guy is lower than the standard cycle. The other common configuration is the regeneration variant. So here I have energy input to the heater reduced, which is going to increase my thermal efficiency. And so what I have here is this regenerator section between the compressor and the heater. And so when flow comes out of my, back down to only one turbine, when it comes out of that turbine, some of it, actually all of it goes into the regenerator, and then some of that comes back into the heater, some of it goes into the cooler like you did before. And so I have this additional sort of junction in my TS diagram. So as I go down to 9, I stop at 9.5, and some of it can be regenerated back into 0.3.5 essentially. So I can go from 9 to 5 to 3.5 instead of going all the way around the cycle. For an ideal generator, this temperature at 3.5 is the same as temperature 9, and the temperature at 9.5 is the same as temperature 3. The regeneration is only possible if T9 is bigger than T3. And so that's going to have to require a low cycle pressure. So pressure ratio is plotted down here. And everything to the right of this line basically corresponds to T3 equals T9. So everything to the right of that, regeneration is not possible. Everything to the left of it, it is. Thermal efficiency, which is plotted on the y-axis, is for the Brayton cycle with regeneration, so given by this formula. 1 minus that pressure ratio to the gamma minus 1 over gamma power. So pressure ratio P3 over P2 to the gamma minus 1 over gamma. That's the same thing as temperature. So this is essentially T3 over T2 divided by T4 over T2 as my thermal efficiency. So again, shown to the right for several values of T4 over T2. As T4 over T2 increases, I get more thermal efficiency, as you can see from these lines. But again, they stop on this line where T3 equals T9, because regeneration is no longer possible beyond that. And so the general turbine engines that we're going to see the next few days are basically what's called a turboshaft variant of the gas turbine engines that we've been talking about generally. Essentially what I'm doing is I'm attaching a shaft to the end of the turbine, and from that I get shaft work out of it. So basically gas turbine engine that's producing just shaft power. So these generally run off the regeneration variant. So I have some inlet coming in into my compressor, into my regenerator. Has some m dot fuel, so fuel added, then being burned. Then end up with a really high pressure. So I have a high pressure turbine. Again, that guy, his purpose is to turn the compressor and keep everything working. Then the air comes out of that and goes into the free turbine, and the free turbine, that's his job is to actually power the shaft. So that's where I get my shaft power out of, is this free turbine. Then getting back into my regenerator, out of the nozzle. So basically what I want from this is this free turbine to essentially slow down the air to a velocity of 0, because if the air has a velocity greater than 0, that's basically losing energy. So some of the energy has gone to increase the velocity of temperature of the air. I'd rather have that energy go into spinning my turbine, getting shaft work out of it. So example, to finish this off, I want to derive an expression for the thermal efficiency for the ideal Brayton cycle with regeneration in terms of this temperature ratio, T3 over T2. So a lot of stuff we did today dealt with the pressure ratio, which is P3 over P2. Now I want to do it in terms of the temperature ratio. So thermal efficiency, again, W dot out over Q dot in. W dot out, same as before, M dot Cp, T4 minus T2 minus T3 minus T2. Q dot in, M dot Cp. I'm dealing with the regeneration case, so I have T4 minus T3.5 instead of T3. Still have my constant pressure processes. So P3 and P4 are the same, P2 and P9 are the same, and then isentropic relationship, so P3 over P2 to the gamma minus 1 over gamma power, the same thing as T3 over T2, same thing for P4 over P9. So I still have the same temperature relationship we had before, but then I also have the fact that for this ideal regeneration cycle, T3.5 is the same thing as T9. And so plugging those into my thermal efficiency, net work out, M dot and Cp all cancel out, T4 minus T9 minus T3 minus T2, and then same thing for the bottom, M dot Cp cancels out. I have T4 minus, again, now T3.5 is now T9. So T4 minus T9, T4 minus T9, that gives me a 1. From the top, I want to pull out a T2. So the top, I have T3 over T2, which is exactly my temperature ratio. T2 over T2 is 1. From the bottom, I want to pull out a T4. So T4 over T4 again is 1. T9 over T4 at the end of that. And then going back to my temperature relationships, T9 over T4 is the same thing as T3 over T2. T3 over T2 is the temperature ratio. Got that backwards. T9 over T4 was T2 over T3, so it's 1 over the temperature ratio. And now what I want to do is multiply the bottom and top by temperature ratio to get rid of this compound fraction down here. So multiplying the bottom by temperature ratio, I get temperature ratio minus 1, which is the same as the top. So I'm left with T2 over T4 times the temperature ratio. This guy cancels out. And so another way to write that, 1 minus the temperature ratio divided by these two values I know, T4 over T2. So that is the basic workings of gas turbine engines. We're going to use these for smaller versions of gas turbine engines called microturbines. Work basically the exact same way, just a lot smaller. So we'll see those over the next 2 lectures.